Now it is recording. Let me share my desktop. All right. Can you see my desktop? Yeah.
Yes, sir.
Good. All right. So let me go to the web browser. So football data UK. Okay. You will get this data set, a website where if you little bit scroll down, you will see the different European leagues are being listed here. So let us take the England. In England, each season 2021 is now currently going on, so you will not get the full data set of the entire season. But 2019-20 season is complete, so we will get the Premier League, Championship, League One, League Two, and Conference. So you can take any of them, and if you click on this, then you will basically get the data set. This is a CSV file. So, and you look at, here is a small, let me try to okay, and here is a node.txt. Okay, if you open it, so open in link in new tab, so it says all the column names and the what the data set, and each column names what it means. So div for league division, okay, then date, time, uh, home team, what was the home team, what was the away team. FTIG means full-time home team goal, and HG is full-time half-time goal, I think. And then all these things are there. All the column names and their descriptions are available. So it's called data dictionary. So they have a very nice, well-maintained data dictionary. Okay. So what I will do, I will just copy the link of this 2019-2020 English Premier League data sets. Copy link address. Okay. Now I will go and I'll just open a script. So I will say data CSV file equal to code. So this is the thing, and then to true. So let me just run this. It's there. Now if I just open from there, so all the entire data set is here. Okay.
Sir, can you please send us the link on the chat box?
Sure. So I'll just copy this and okay. Just a minute. Where's the chat box? Chat. I just sent it. Okay. All right. Okay. Now you have the data here. So the first division is E0 means Premier League. E1, I think. So since this is Premier League data set only, so all the values will be E0 only. So this first column is not of not much of our helpful thing. But if you take also the say Champion League and append the Champion League data set, then your data set will have a E0 and E1, which will be your different leagues data you can append, because they have maintained the same column names. Date, time, home team, away team, full time, FTHG is the goal scored by home team. That means on the first match was happened between Liverpool and Norwich. That was the first match on 2019 season, and home team scored, that is Liverpool scored 4 goals and away team scored 1 goal. Okay, in the full time. That was the full time result. And here I think there is a full time result. H means full home team 1, A will mean away team 1, and D will mean it was a draw. So FTR has a 3 possible values. It's a basically string variable. It has only 3 possible value, HAD, and FTHG is how many goals scored by home team during the full time. All right. Now, what I'm going to do, I will just FTHG.
So what does this header equals to true do?
Means if you when it will be read, it will, if it has the column names, it will be read by the column names. But if you say the header equal to false, then what it will do, it will take the first row and treat the first row as the column name. Okay.
I mean, one of the entries as the column name. The first entry as the column name.
Yeah, first row of the entire data set will be treated as the column name. But if you give header equal to true, then it will be considered that, yeah, sorry, header equal to true means yes, in the data set, first row is the column name.
Okay.
And if the header equal to false, then what will happen is it knows, you know that the data set does not have a column name. It will just assign V1, V2, V3, V4. And then later you have to assign the column name separately.
Okay.
Okay. Header equal to true means the data set itself has a column name. That is the first row. And R will treat the first row of the CSV file as the column name. Okay. Achha. Next, what I'm going to do, data dollar FTHG. So don't worry about writing this in parallel. I will share this code. I shared the last code, right, with you guys. Did I share that?
Yes, sir.
Yes, sir. Yes.
Yeah, okay, good. So now if I just do that, so this is in the first match, home team scored 4 goals. In the second match, home team scored 0 goals. In the third match, home team scored 1 goal. That is how it is. Okay. And if I actually say in row of data, that is the 380. That means there are 380 rows. That means 380 matches were played in the season of 2019, 19 and 2020. Okay. So similarly, you can do LENGTH, length of FTHG to the 380. So either you can take data as a, one more thing you can do. You can do say STR. What is STR? It's basically structure. It will tell you what kind of data structure object is there. So R is an object oriented language. Everything will be considered as an object. So data is an object to me inside R. But I don't know what kind of data structure it has. It could be a data frame, it could be list, it could be array, it could be vector, it could be heap, I don't know. So I'll just say str data, it will tell me the data structure. So it's saying it is a data frame. So if you give a CSV file, read.csv in data, so it was the structure of the data is, it is a data frame, data.frame. It has 380 observations, means 380 rows, and 106 variables, means 106 columns. So in R, each column will be considered as a variable and each row will be considered as an observation or instances. Okay, clear? Anybody have any doubt? Okay, all right. Now, out of these so many variables, we will first we will take baby steps. Okay, so what we will do, we will start with small one variable. We'll first consider this FTAG, full-time number of goals scored by home team in full time. Okay, now if I assume the number of goals scored by a home team is a random event, or the goals, any goal scored by, it's few, just, because same match, if it is being played another day, the result will be slightly different. Maybe the same team will win, maybe it will be a draw, maybe home team will score more goal or less goal. We all know that the same team, if play the same game another day, this, it can be a little bit different result. So we can assume that the number of goals scored by the home team will be slightly different. Now, if this is my, if these are the, if I see that these are the count, I mean, we can see these are the integers. Number of goals scored by the home team cannot be 4.5 or 3.2. Either it will be 3 or 4 or 5 or 0, 1, 2, 3, 4, 5. So the number of goals, so first we want to model the first variable, that is FTAG, the goal scored by home team in full time. Okay. Now, question is, the first thing we can do is couple of things. First is, since it's a count variable, we can compute how many out of 380 matches, how many match there were 0 score was done. So one way of doing it is just create set table and FTAG. So that will give us a sometimes what is called frequency table. Okay. Let me just so this is my entire data, 380 matches. 380 matches. Out of these 380 matches, there are 8. If I just keep counting 0, 1, 0, 2, 0, 3, 0, if I keep counting, there are 84 such matches where home team scored 0 goals, means they did not able to score not even a single goal. There are 125 such matches out of 380 matches where home team scored only 1 goal. Okay, and there are 99 such matches where home team scored 2 goals, like 3, 4, 5. There were not a single match. It was where home team scored 6, 7 goal, and there was only one match, random freak match, where home team scored 8 goals. Okay. Now we can try to even make a bar plot of it. Okay, so what I will do, we can do it in 2 ways. There is a simple something called bar plot, and if I just give this, it will just create a bar plot. Okay, so this is simple one way of doing it. Another way of doing it, I can just use Ggplot2 library. Okay, if you don't have Ggplot2, what you can do, you can go to package. Here you can see on there is a files plot packages help. You can go to the package, then install and write Ggplot2. So you choose that and then just make sure your install dependency is correct, clicked. This will may have some dependent thing that you need to be clicked. If you don't do that, it will not install the full ggplot2 the dependence thing, and then your ggplot2 will not run properly. And then you just hit the install, so it will install your ggplot2. It's a little bit big package, so you have to be a bit careful. Okay, so it might take few minutes actually. So ggplot2, so I have it here. And then there is another way of using ggplot2. So simple bar plot, I think, is there in base package. I think bar plot. It's in the graphics package, which comes default as a default setup. Okay, and Ggplot2 is I can do the quick plot. There's some quick plot data equal to FTAG, and then I think it will be geom is equal to bar. I think it will be, let me see. Okay. Where?
Sir, you can use the like if you're passing a vector, then you can use the aesthetic function.
Right. So how you can do that? Let me just check it out. What was that thing? Okay.
Just remove the data part and then use AES and then x equals to the vector.
I think there, if you go there in the ggplot2, there was a nice, if you go down here, yeah, there is a Ggplot. All right. I think if I just use this and data equal to data and then geom equal to bar, this will work. I hope so. Let me see. Yeah. Okay. So this book is very good that I have shared with you on the visualization thing. So you can, either you can use this one or you can use this one. Anything is fine. But we will keep learning more and more about this, how to make nice plots and stuff like that. All right. Now my question is, if you look into the, which is called a frequency table, this is my frequency table, or this bar plot of the frequency table. If I have to think of a probability model, which probability model you'd like to choose? All right, let me see. You can write it on the chat box. Virup is saying Poisson model. All right. And why Poisson model? What is your What is your logic of choosing Poisson model?
So because like it's almost as a rare event, and like the count is decreasing significantly as the uh, say the frequency. I mean, the frequency is significantly decreasing as the value is increasing.
Okay. Okay. Binomial is another option. All right. Anything else?
Sir, I think binomial because we did not take assumptions over there. I don't know.
But binomial has a limited range, right? Over here, the number of goals can be effectively anything,
But
any integer.
on the basis of
Yeah.
data, we can see there are only there are only a few bins are there. So it will be like an additional assumption to say that there could be more goals.
Yeah, I mean, as per the domain knowledge of the football scores wouldn't go to like 9, 10, or 50.
Right.
Wouldn't. So we can have a assumption over there.
So,
Okay. Yeah.
so can we use binomial because the reasoning I'm talking about, because the probability of success is same in every trial, like it's half, whether it will win or not. So like that, like can this be a valid reasoning?
Um, Probability of success means probability of scoring a goal.
Yes.
Why you are calling it half?
Like whether it will score or it will not score. So like half.
That is an
But
event.
the scoring
Score
of the goal
or
depends on
not
other
score.
factors also.
Say it again.
Scoring of the goal depends on other factors. If someone scores 2 goals, then the opponent will also be strong. I mean, the defending team will also be strong, and such factors will work, I guess.
Right. So that means, see, there are two things. One is scoring a goal or not, but scoring a goal with what probability is a different question. Probability could be more than half, less than half, anything. It can happen many things. Okay. And, but scoring a goal or not is 0-1 case. I can score, but I can score a goal with probability 0.8. I can score a goal with probability 0.5. I can score a goal with probability 0.2. So probability could be different depending on my ability to goal, depending on what how good the team is, and what is the playing conditions and stuff like that. Okay, so the chance of scoring a goal can differ. So that is a parameter of a model, or probability of that's a different thing. But score a goal or not, it's a okay. Even if domain knowledge tells you that count cannot be greater than say 10, the frequency is significantly less on the end, suggesting that it is more of a Poisson pattern. Yeah, I would prefer to go with Poisson pattern. Okay, I would prefer to go with Poisson pattern over binomial. I'm not saying binomial will not work. You can choose n equal to 50 or 100, and probably binomial and Poisson will behave similar. I'm not saying that it will not work, but I would prefer to choose Poisson. Any other model?
So,
Mm-hmm.
sir, if by assumption we assume that the probability of scoring a goal or not scoring a goal is same, so in that case, can we use binomial?
You can choose binomial. I have no problem. You can choose binomial, uh, but as I said, that theoretically, number of goals scored by home team could be 100 plus. Just imagine, Manchester United is playing against some Indian team. I'm just asking. It never happens, but suppose it is happening. And
Yes.
how many goals you can score? Whatever you set up your n, it will be more than that n,
Right,
right?
sir.
So binomial will be in that sense. I'm talking about a really, really, really rare chance. So in that case, binomial will be always gives me a upper bound. that n, number of goals cannot cross n. But but theoretically, number of goals could be anything, right?
Yes, sir.
So okay, one choice is skewed normal.
Sir,
Skewed
are
normal
you
is continuous
about one thing?
distribution, like.
Yes, so skewed normal is a continuous distribution. Means when my variable is continuous, right? That time I can use skewed normal. If I'm trying to model, say, height, where I know it is a continuous, or I'm trying to model blood pressure, or in terms of games, something like that. Having said that, you can, I have seen people do use normal or skewed normal or gamma or log normal, even in cases like, say if you're modeling runs in cricket. Runs in cricket, typically it's a big number, right? 200, 250, 110 and stuff like that. That time people do use normal distribution kind of thing. I have seen that. I'm not saying that will be the thing, but yeah, but that means you are making an assumption that you are treating the count variable as a continuous variable, as if a continuous variable. Okay, and so there are which one? Okay, hold on. Okay, Ayush is asking, isn't it too much strong condition in case of Poisson? Why it is too strong
So
condition?
like in if we take binomial as someone was pointing out 0.5 probability, so definitely that should not be the case, because if the probability was 0.5, the distribution would be centered, would be symmetric. But since
Correct.
we can see that it is like it is shifted to the right and around 1, so I think it seems like a good choice. If we can, I mean, there are other options also, but if we take binomial
Okay.
distribution with probability definitely around 0.1 or 0.2, something like that. So
Correct.
in that
Correct.
case, the distribution would look somewhat similar to what the data is showing us.
Correct. So why not we try? So these three suggestions have come, and we will try all these three and see which one is more sensible. Okay. We'll try all these three. So, but I'll start with Poisson. Okay. So one, okay, Chandrashis is saying the mean and variance being almost equal, convincing for Poisson. Okay, fine. Let us try what is the mean of the variable. Mean is 1.51 and variance is 1.55, very close to each other. So this could be a good case for Poisson. Okay, so I can say that, okay, so Poisson is a good candidate so far. Looks like this tells me it's a good candidate. Okay. Another suggestion, negative binomial. Well, this is also a possibility. See, we have now learned that all models are wrong. Remember that all models, whatever you are trying, it's wrong. So we have to choose a model which is best suited to our situation. Okay, so negative binomial is also a possibility. Negative binomial, and we will try all these models. Okay, all right, let us try to see. So we'll start with Poisson, and Poisson will be more like, so now we can say that, okay, so suppose FTAG, this guy follow Poisson lambda. A Poisson distribution with parameter lambda. Okay. So how I decide that? So basically that means I'm saying effectively my probability x equal to 0 will be exp minus lambda times lambda to the power, say, x. Let me just put, yeah, let me just put k instead of 0. I'll just say k by k factorial. So this is my probability. If I just k equal to 0, I put then I'll get the what is the probability of that. So first thing I have to make some educated guess about lambda. So what kind of educated guess I can make about lambda?
The maximum likelihood estimator or moment estimator.
All right. So there is somebody saying maximum likelihood estimator. Another is moment estimator. Okay. And I'll come to maximum likelihood estimator little later, but let us discuss the moment estimator because it's a simple thing. So what is moment estimator?
Mean.
Mean. How you know that it is mean? How do you know it is mean? Mean means what? I mean, you mean population mean or sample mean?
Sample mean has to be sample mean.
To be sample mean. And why it is so? Because we know the population mean expected value of x if x follow Poisson distribution. So that means I would know if FPHG is really follow Poisson distribution, FPHG is equal to lambda. I know that. So then my population mean is lambda. So I would say that, all right, my sample mean is approximately equal to lambda. So that is what that is the intuition behind taking the moment estimator. All right. So what I will say, I'll say that lambda, lambda hat is equal to mean of FPHG. Okay. Now I have, which is 1.5159. So that means I'm saying that FPHG is following Poisson 1.5158 maybe. Okay. Now, how do I figure out if it is a really good one or bad one? I don't know. So tell me this. So one thing I can do, so there are 380 matches were played, correct? So what I can do, I can try to see that if it was really playing the, it was really following the Poisson distribution, how many expected number of matches I would how many number of matches I would expect out of 380 matches to score 0 goals or 1 goals or 2 goals. So that I can try to figure out. So what I will do, I'll write PMF for Poisson, function called PMF Poisson. Okay, there is a function called D Poisson. Okay, D Poisson. Or D points, I think. D points, yeah. you can, which basically gives the PMF probability mass function for Poisson. Okay, but I'm not using it for purpose just because I want to give you the maximum intuition about how the things work. So I will write a small function PMF Poisson. So I have to give X and the lambda. So basically that is what, or K and lambda. All right, so I can just say. So if I just say PMF Poisson, X equal to, what was my FTAG first value? If say first value is, so remember that indexing in Python work starts from 0 and in R it starts from 1. So when I give 0, because I was working in Python for a while and first thing it came in mind in 0, so I gave 0, it gives me integer 0 or something like that. And when I give the 1, then it gives me the first value. So remember that. And then lambda equal to lambda hat. So what is my lambda hat? It is 1.51. So it will return. I have to run the function. Yeah. So it's saying that if lambda is the lambda hat 1.515, then I will see a match where home team scores 4 goals is 4%, about 4%. Okay. Now what I'm going to do, I'm going to say 0 to say up to 10. So basically 0, 1, 2, 3, 4 up to 10. And so these are the probability of, so if this particular variable FTHG full-time, the goal scored by the home team, really follow Poisson distribution with parameter 1.515, then the goal scored by the home team, 0 score is, this is the probability. 1 will be this 0.31329, something like that. Okay. So what I will do, I will just say PMF probability mass, probability hat equal to, say, round, maybe 3 digit, I will say. Okay. And 0 to 10, I'll say C bind. Okay. So 0, that means if home FTAG, this particular variable really follow Poisson distribution, then it will be on a particular match, the home team will score 0 goals, they will fail to score any goal. The chance is 0.22. If they score only 1 goal, that chance is 0.33. They will score 2 goals, that chance is 0.252. In this way, they are dropping. And after 7, the score is, and the chance is almost 0. I mean, they must have some probability, very large, but I'm just rounding out at 3 decimal places. So they are rounding off to 0, 0, 0. Okay. Now what I will do, I will calculate the expected frequency. So how I will do that? Expected frequency is probability hat times how many matches were played? Do you remember?
380.
380.
380. So I will write 380. Sorry, 380. Now what I will do, I will say this is my expected frequency. So this is the expected number of matches that I would see if it really follows normal Poisson distribution. And what is the original thing? Observed frequency was,
We got it from table data.
right. So in 0, we observe 84. In expected frequency, we are getting 83.6. So almost matching. 125, it is 126. Observed, we observed 99 cases. In case of 2, expected frequency is 95.76. If we round it off, 96 it will be. In case of 3, we are observing, we observe 47 such cases. In expected frequency, it is 48.26. In 4, it is, we observe 16 such cases. We observe 18.24 such cases. Expected frequency is 18.24. 8 is the 5, is 5.7. And then for 6, we are expected to see at least 1 or 2 cases, but we have not, in the observed cases, we have not any such cases. Then 7, 8 was 0. These are rare events. So, but we have observed 1 such case. So looks like Poisson is a really good case. Okay. All right. So Poisson looks like Poisson is really good case. Let me save this code. So I just save it as football data access .r. Okay. So we'll write a comment. Looks like Poisson is a really good candidate for the goals scored by the home team in English Premier League. It doesn't mean that this will be the same for Champions League or the Bundesliga or any other league. In English Premier League in 2019-2020, we found the home team's goals scored by the home team tend to follow a distribution which is very closely to the Poisson distribution. Behaves like a Poisson distribution. This is very possible case. Now here we have used method of moment estimator. The method of moment estimator has certain limitations. Limitations is that for most of the method of moment estimator available only for very small set of probability models, like Poisson, binomial, normal, maybe log normal or something like that. But it's very difficult to actually, after a certain level, it is very difficult to develop a moment estimator. So on the other hand, likelihood estimator are much more easy to, not easy, I would say likelihood estimator is a template. You can think of it as a template which works for any model or every model. From a simple Poisson model to deep learning model. Even the deep learning models are being fit using likelihood estimators. Okay. Of course, not plain vanilla likelihood estimator. There are certain modifications are required because these are very difficult and complicated models, which we will teach you in DMML course and AML course, advanced machine learning course. But likelihood estimator is something, likelihood method is something which will be used from a simple Poisson binomial model to a very large complicated black box model. So you can think of it as a template. So I guess it is being taught to you. Is Professor Ramuti taught you the likelihood estimator?
Yes, sir. He mentioned it in previous class.
Okay.
But I think that he didn't cover entirely the topic.
Okay. Maybe he will cover, but let me, I mean, there is no harm hearing twice. So you can hear it from Professor Ramuti as well as you can hear it from me. So let me spend some time on likelihood estimator, and then I'll move to the other models, binomials, Q normal, and negative models. Okay. But let me first go to little bit discuss on the likelihood models. Okay. And I may take little bit, so I will slow down here because this is one of the most important concept of data science. So unless all of you are on board, I am not going to take any other new concepts. So I'll be going very slow here. So likelihood estimation. Okay. So I have 380 data points or sample. My sample size is 380. For the time being, let's assume I have only one sample, the first observation. Suppose the first match has happened and the you have only one data points, 4. Okay. Now, if it is being said to you that this particular variable follow Poisson lambda. What will be your educated guess? Of course, one, okay, I'll not tell you anything. I don't want to lead you. Just think about it. What will be your educated guess?
So since only one observation is given, either we can accept our given assumption that it follows Poisson.
No,
Like
I'm just saying that no, you just assume it is Poisson because remember that I told you that all models are wrong in any way, end of the day, right? I'm going to try as many models as possible, and you're trying with Poisson model, you have 1 data points. If I ask you to make an educated guess about the lambda, the parameters of the model, which model you would like to guess? I mean, with how you want to make that guess?
So sir, lambda will be equal to that one observation.
Why? Suppose you don't know the method of moment estimator also, okay? Or you know that, but why? You are saying from, okay, that is from method of moment estimator, right? I have one sample, the sample mean of that one sample is its sample itself. So that is my thing, but that is method of moment estimator. Suppose you don't know the method of moment estimator, or it's such a difficult model that I'm just saying that you have not aware of the method of moment estimator.
It
Sir,
has the highest likelihood that one observation.
Yeah, what is likelihood then? Then question is, what is likelihood? What is likelihood? That is my basic question. What is likelihood? So I will make first what I will do, I will make an educated guess about lambda. Suppose lambda is 1. First of all, I know what is the range of possible values of lambda. Lambda lies between 0 less than lambda less than infinity. Right? It's on the positive real line. That I do know. If you look into the textbook, you open your textbook, you check for the possible range of lambda. Lambda is a continuous parameter which takes value. It's a continuous parameter variable. It takes value between 0 and infinity. That is the range of lambda. Now, I can choose lambda, possible lambda. One possible lambda could be say 1. If lambda 1, possible value of lambda is 1, then what is the probability that you will see this data? I can simply take this, compute this, and I can just put x equal to whatever that value. What was that value? 4. I can just say x equal to 4 and lambda equal to 1. So if the value of lambda is 1, then I will see this data x equal to 4 has probability 0.01, chance that if the true value of lambda is 1, then the chance of seeing this particular observation x equal to 4 is only 0.01, 1%, 1.5% chance. All right. What about the value of lambda is, say, 1.5? Now, observing this particular data is chance is 0.04. Now, if I ask you which lambda is likely lambda, given the data that you have in your hand, x equal to 4, which lambda is more likely lambda?
1.5.
Yes. All right. What about 2? 0.09. Now 2 is even better than 1.5. So what I can do now, well, I can create a lambda series of, I can define a series of lambda values. Lambda start, sequence, say between 0. I don't want to take the 0 value. I want to take 0.001 to say up to 10. Length. So 100 values I have defined. These are all possible values of lambda. And I can compute if this is the possible value of lambda, then what is the chance that I will see this particular data? Okay, I can compute that, nobody can stop me. So if you do that, so these are the corresponding probability. Let me just round it off. That will be. So these are the corresponding probabilities. So let me just wind this, then it will be better. All right. So these are the lambda star and these are the corresponding probability that I'm getting. So that means if I take lambda equal to 1.011, then probability that I may see that particular data x equal to 4 is 0.016. If I make an educated guess that, okay, 1.415 is the possible value of lambda, then I may see that particular data x equal to 4 is 0.041. Okay. So these are the possible probabilities of seeing that particular data. And given these probabilities, this will tell me that, okay, which is likely value of lambda. So so if I have to compare 1.415 and I have to compare 2.82, 1.415, if the value of lambda is 1.415, then I will see that x equal to 4 is 0.04. But if the value of lambda is 2.52, then I will see that particular data is 0.136. Okay. So that means 2.526 is more likely, 2.526 is more likely than 1.1 or 1.516. So that is why this, now what I can do is I can simply plot them. Lambda star, and I actually, let me just put these probability. Maybe I will just say like of this, and then so now it looks like a function, right? For this is, remember that this is not a probability function. This is not a probability function. All I am doing that, I have a data, I have only one data is saying x equal to 4. That is what I all observed. Now, given that data x equal to 4, what is the possible value of lambda equal to 2? The likeliness of seeing that lambda equal to, seeing that data x equal to 4 for lambda equal to 2 is somewhere here. That is the likeliness. Whereas if if the x equal to 4 you have observed, then the lambda is near 4 is somewhere here. The likeliness of that lambda is somewhere here based on one observation. Okay, and this function, if you just join this and this function, you can clearly see that this probability is becoming this is not probability, but this is, if you join them with the small straight lines or join the points, it will become a function, and this function is called likelihood function. Remember that this is not a probability function. Okay. All right. Now, all of you are with me. Anybody have any question? If you're guys okay with me, then I will move to the next step. This is the step. This was the step 1 to understand the likelihood function. Now I will make your life little complicated. I will consider two observations. Okay. If you have your data consists of two observations, if T and G 1 H2, you have observed 4 and 0. What is the probability that you will see these data? You can you can say the first observation that you have observed as a x1 is one random variable, came out of one random event. And this is another random variable, came out of another random. It is the observation that you are observed, but this is the first case, and this is the two random variable, and 4 and 0 are the realization of two random variable. If you repeat the match, you go to another season, the first match may have another value. For instead of 4, it could be like 1 or 2 or 0, something like that. But suppose you have two random variable. Okay. Then what is the first problem you will face? If you have two random variables, so first thing you have to define is a joint distribution of x1 and x2. Okay. Another level of, so joint distribution of x1 and x2, where x1 is a count distribution, count variable, x2 is also a count variable, like 0, 1, 2, 3, 4, 5. We really don't know many bivariate distribution which actually follow which a count variable and follow a joint correlated distribution. So to make our life simpler, we will make this assumption that x1 and x2 are independent. All the assumptions you will see independent, identically distributed, just to make the life of data scientist simpler. So sometimes you have to justify that whether that independence is correct or not. But if I do that, then my life is simpler in a sense that P of, I can just now write x1 times probability of x2. Now, probability of x1 could be the simple probability mass function of Poisson distribution. P of x2 is another probability mass function of Poisson distribution, and my life is simple. and I will make identically distributed so that X, one can come up and say that, sir, why I can say it like this, X1 for the Poisson, lambda 1, and X2 for the Poisson. They are independent, but they have separate lambdas. And lambda 2. Now you have two different lambdas. So every time you have to estimate a separate lambdas. That will be a really hard thing. So to make our life simpler, we just say that, okay, they are identical. They're coming from identical distribution. Okay. If they're really coming from identical distribution, then I can just assume Poisson lambda for X1, Poisson lambda for X2. And in that case, I can just multiply them and my life is done. We are good. So if I have to do that, so what I will do, FTHG 1. What time is it? Okay, we are over time, so I'll conclude that very quickly. So I have two values, and then I need to multiply them. So I have to take product. So first, I cannot take lambda star, say 1. I take one value at a time, and then, so these are the two possible values. If I take lambda equal to 1, then I have seen the value X equal to 4 has a chance 0.01, and I have seen the value X equal to, what was that? 0, I think, is 0.36. Okay, so these two probability, I have to take the product of them. And this is my likelihood function. Okay. So this is my likelihood function. Well, so that means if I have seen this particular data 4, 0, the chance, if the lambda equal to 1, then the chance that I will see this particular combination 4, 0 is 0.005. If I choose 1.5, the chance that I will see this particular data 0, 4 and 0 is 0.01. So I would prefer 1.5 over 1. Same idea. Only thing, now I am using 2 data points instead of 1 data. So that's how we define our likelihood function. Okay.
Excuse me, sir.
Yeah.
We are preferring 1.5 because it's giving a probability of 0.01, which is closer to the actual data set also.
No. I'm not, I'm just took 1.5 ad hoc. You can take 2.5 also. If you take 2.5, you will get something different. Yeah, 0.01, 0.0109. So what I will do again, I will do a lambda star now. And we'll put it there for each. So what are the lambda star? Bunch of values between 0 and 10. These are the possible value of lambda. and I'm going to compute their likelihood values, and lambda star plot the lambda star against likelihood values. So it's
So you plotted lambda star with lambda star.
sorry. What is the problem? Why it is different? Let me check. Okay. Oh, okay. Yeah. So I have to do it in a loop. Sorry, because it's creating the product. All right. It's creating a product. So I for I in one each to length of lambda star. So I, and I have to say like equal to, I have to create a vector out of length of lambda star. Then, yeah. So now this is the, or I'll just say PCH. So this is the likelihood function of of observing that particular data 40, okay, observing that particular function 40 for different choices of lambda star. So this is my likelihood function for the data of size 2. So that means if I choose this lambda equal to 4, then this is the chance that I will see that particular data. This is the likeliness of this lambda equal to 4. And then if I choose a 3 is here, and if I compare 3 against 4, then this is the likeliness of seeing lambda equal to 3 or lambda equal to 3 if to see that particular data 4 and 0. Okay. So that is the idea of the concept of likelihood function. Now, same thing, if I can do it for 2 observation, I can do it for n observation. All I have to do, I have to make 2 assumptions, independent and identical. And then I can just simply say that, okay, probability of x1, the joint distribution of x1, x2 dot 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 xn is equal to probability of x1. To make our life very simple, x2 dot 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 product of xn. To make our this, remember that we are making this assumption. This is a part of the model. This assumption is now part of the model, independent and identically distributed random variables. Now my question is, if try to, whatever I have done it for 2 variables, now you try to do it for 380 variables. You don't do it for, you just don't take it, you just don't need to do it, you just take the entire variable, the vector, and you will run into, inevitably you will run into a problem. Okay, what can you tell me what problem you will run into? In fact, if I just run it, you will get the sense. And after that, so if I just take, say, and if I just take lambda equal to say 3, so this is my data and this is the lambda equal to 3. So now I'm trying to compute the PMF values, that these are the corresponding PMF values for each of the product, each of the P of x1, P of x2. So I'll take the product of all of them. And product will be 0. Why it is 0?
Very small values are included.
Is it so?
So because there is one observation with 8 and whose probability would be 0, maybe.
There is no 0.
Anyways, we are multiplying these numbers which are all lesser than 1
Yes.
and above 0. So it will tend to 0.
Yes. So exactly, these are all probabilities. So these values are between 0 and 1. If you multiply lot of fractions, what will happen? They will tend to 0. Correct? If you they will start tending to 0, and there is something called floating point error, that there will be, after a while it will just round it off and they will make it 0, hard 0. Okay, so that is a problem for us. How can I solve this problem? Any idea?
We can multiply each thing by, let's say, 10 and then divide by 10 to the power whatever the length.
So we could take the log.
We can take a log.
Exactly, we can take a log and make our life simpler. But if I take a log, then it will not be a product, it has to be a sum.
Addition.
Correct? So if I take log, then it will sum of the log. So I can take log and instead of product, I will take sum. Now you see, it's a number, it's at least not 0. It's giving me the number. And now I can, what I will do is, I will define log likelihood, log like equal to so I'll put it in there. And now I can plot log likelihood against lambda star. So the log likelihood looks little weird, but it's something like that. Maybe we can, what we can do, we don't need to take the value of lambda till 10. What we can do, we can just, maybe we can just take the lambda value of lambda to be where we define the lambda star. here. Defined up to 10. Maybe we just define lambda, redefine lambda star up to 5. So that we will have a little bit more value here around 0 to 1, so that this part will be a little bit better for us. But anyway, so near about, this is the place where it is maximizing it. So one last thing I would like to do, and then we'll go for lunch. Lambda star log likelihood. I will just put them in something called cbind dot data dot star equal to lambda star and log likelihood equal to log likelihood, and I'll just put it in result. So I put it as a data frame. So head of the result, if I just say, so lambda star, for different values of lambda star, I calculated the log likelihood values. Okay. All right. And then what I will do, for which value of lambda star log likelihood is maximum. So which dot max res, I think it's I think I'm doing it right. I don't know. Let me just check. Oh, no. Okay, so it's saying that index. So if I just have 100 values, 31st value is the one for which I get the maximum thing. So I'll say that ID equal to the I. So this race is a data frame which has 100 rows. Okay, so if I just say race dollar, ID comma so 1.5158, at which log likelihood is maximum. Log likelihood, it's being observed out of 100 observations. So my likelihood estimate is 1.515. And for Poisson distribution, mathematically closed form solution is also available. Do you know that?
X bar.
This is, and that is? So we'll do it maybe next time, or I will just hint you where you can find it. Actually, if you just, I think it's available even in Wikipedia. So let me just see. Just go even Wikipedia. You'll find it. Just I think. Approximation. Parameter estimation, yeah. So the maximum likelihood estimation. So what they have done, you can see, this is the joint distribution that they are writing. Okay. So product of each of the PMF, that's what we are doing. And then we are taking the log. They're exactly doing the same thing. Log, that gives you sum of log of the PMF. After doing the thing, it's came down to this. So this is my log likelihood function. This is what exactly we computed here. This is exactly what we computed, sum of log of the PMF. And this is exactly what they did. Sum of log of PMF. That will give you log likelihood. Then you differentiate the log likelihood with respect to the lambda, equate to 0, will give you the maximum. You solve it, and that gives you the sample mean. This is the maximum likelihood estimate for the Poisson distribution. Okay. And if you take the mean for FT, which is 1.15515. So we can see that likelihood estimate is very close to that. So this is a numerical solution. What we got, this is numerical solution, and this is the exact analytical solution. Okay. So I'll keep continue on that. And in the Moodle, I have given in this book, chapter 11, they have introduced the Ggplot2. You can have a look. So in the Ggplot2, in plot, you will see a plot is basically a function of some data, some aesthetic and geometry. And the plot, typically it takes two forms of data, either table, which comes from a tidyverse package. Another is the data frame, which we got a little bit of used to with. Table also it's a particular data structure that comes with the tidyverse package. We will get used to with that. Aesthetic, when it talks about aesthetic, it's basically position, size, color, shape, transparency, field, scale, that you have to always play with that, these parameters, and come up with a little bit. So there is no much thing you can do. And the geometry is, do you want to do a histogram, box plot, scatter plot, what kind of plot you want? And little bit detail is given here. So I have taken it directly from this book, Scredo et al. This book. And so Ggplot2 is basically built on architecture called grammar of graphics. In the grammar of graphics, they basically focus on 7 layers or 7 elements. Coordinate system. Do you want a Cartesian map or polar presentation or map projection? These are the typical 3 projection they are looking for. Geom stands for geometry. What kind of geometry you want? So you want a point plots? Do you want a line plots? Do you want a polygon? What kind of geometry you look for? Aesthetic is position, size, color, shape, all these things. Scales. Do you want log scale? Do you want color? I mean, what kind of scale you are looking for? Then stats. Stats is like counts, mean, median. Do you want to fit a regression line? Do you want to fit a smooth spline? Whatever you want. Facets. Facet is within the same data set, you can create 2 sub data set. And for each data set, you can, so for data set, you sub data set 1, you create a box plot. Sub data set 2, you create another box plot, and you put them in the same graph to compare 2 box plot side by side. So that is what typically the facet does. Typical case. Theme is basically what kind of theme you want in the background color. Do you want a dark theme? Do you want all these things? So this grammar of graphics is the main code structure based on which the entire thing has been developed. So we will keep continue on that. So, okay, thank you very much. And see you next week. Anybody have any question, by the way? Yeah.
So ggplot is